All right, so welcome back to my BC Calculus series. Today we're continuing our unit on applications to derivatives, and we're going to cover mini topic 3 and mini topic 4 today. So my plan was, because yesterday we did 2 mini units and we did a good job, my plan was to do 2 mini units a day, finish the unit by tomorrow, and do some BC Calc FRQs on Friday. But going through the textbook for these two chapters, I may have bitten off a little bit more than I can chew or than we can chew.
Yeah.
So worst case scenario, we'll take some more time on it. And yet again, if we take like the majority of class to do on Friday to like learn content, that's fine too, because the FRQ won't take that long, and also we could always push the FRQ to some other day. But I'm not too concerned. But I have the lesson plan for today. We'll get through as much as possible. If we can get through all of it, that's great. But if not, we'll just gauge where we are at the end of the lesson.
Word.
Cool. All right. So as always, we have our topics of discussion. I'm gonna do something a little different this lesson. What I normally do is I normally outline the topics of discussion and then I just kind of forget about them. I'm gonna outline the topics of discussion now, but at the end of the lesson, I'm gonna come back to it so you can see how like these topics you didn't know at the beginning of the lesson you now know. So we're gonna talk about the first derivative test, extrema at endpoints, which is something we talked about yesterday. Dylan's step-by-step guide to finding a function's extrema, patent pending. Breaking a function into intervals, concavity, concave up versus concave down, inflection points, the second derivative test, learning about a function from its derivatives, discontinuous derivative, continuous function. What does that mean? Modeling and optimization, how to approach these types of problems. Modeling and optimization problems are a class of problems, and we're going to learn how to approach those. We're going to do some modeling and optimization practice problems, and we're going to do some examples of modeling and optimization from economics that the textbook includes. And when I was tutoring Johnny, he also had some problems for economics, so I think it might be useful to at least know the very basic calculus terms in economics, because I don't know if it's going to ever come up in calculus or BC Calc, but it might because it's in the textbook and I saw Johnny doing it. So I've included it in the textbook just to be on the safe side.
Okay.
Or on the slideshow. All right, cool. This looks like a lot, but we're going to go through it really slowly. The first derivative test for local extrema. We're going to go through this very slowly. All right, a callback from yesterday. And if you need me to draw this out, just let me know. But I'm just going to say it, and you tell me if you remember this from yesterday. Yesterday, we established that local extrema only occur at critical points. But not all critical points are local extrema.
Yeah.
Does that sound familiar?
Yep.
All right. It's pretty easy to calculate critical points. Just find where the derivative is 0 or undefined, right? If we have a function, we know how to calculate its derivative. So if we want to find the critical points, we just calculate the derivative and see when the derivative is equal to 0 or doesn't exist.
Yeah.
All right. But once we have all the critical points, how do we know which ones are local maximums or minimums, right? Because if we have a list of all our critical points, some of them might be maxima, some of them might be minima, some of them might be neither, right?
Yeah.
So if we have our list, how do we know which ones are which? And the solution is to use what we call the first derivative test, all right? And I'm going to go onto Desmos to illustrate the concept of the first derivative test and kind of let it pop out naturally from our exploration, okay? So let's go back to the function x cubed, which we looked at the other day as an example of a location where the derivative of the function is 0, but there is no maxima or minima there. So we have a critical point, but there is no maxima or minima there. Okay?
Yep.
So if we were just given this function and we found its critical points, right? How would we know whether this critical point is a maximum or a minimum without looking at the graph, right? Obviously, looking at the graph, we can see it's neither. But how can we extrapolate more information to determine whether it's a maximum or a minimum if we weren't given the graph, all right? And the thing is, we have to look at the function around that point, all right? I want you to tell me the answers to the following questions. What is the slope of the function as it approaches 0 from the left? Like, what is the sign of the slope? Is it positive or negative on this side?
Positive.
All right. And then on the right-hand side, what is the value of the slope? Is it positive or negative?
It is still positive.
Exactly. All right. So in this example, we have a critical point, but on either side, the derivative is the same side, or the same sign.
Yeah.
Okay. So we have a critical point, but the derivative on either side is the same sign, and that seems to give us a not maxima or not minima. It seems that we would have a critical point that is neither, because the derivative is the same on each side.
Okay.
Now, let's look at x squared. All right. Would you agree there's a minima here? There's a minimum here?
Yeah.
What does the derivative look like from the left-hand side? Is it positive or negative?
It is negative.
What does the derivative look like from the right-hand side? Is it positive or negative?
Positive.
Exactly. So do you notice that when there's a minimum, there's going to be a sign change? The derivative is going to change signs around the point. All right.
Okay.
We're going to have our derivative equal to 0 at the critical point, but in order for it to be a minimum, the derivative has to change from negative to a positive around it. All right. Similarly, if we had a maximum, the derivative would have to change from positive to negative around it. All right. Which makes sense. If you have a maximum, the slope is going to be positive until it gets to the point, and then it's going to be negative and start decreasing. Otherwise, it wouldn't be a maximum.
Yeah.
If it's positive on both sides, well, then it's just going to go up here, and it's not going to be a maximum, and it's not going to be a minimum, because there's a values lower than it over here, and values higher than it over here.
Yeah.
So, in summary, in order for a maximum or minimum to exist at a critical point, all right, the derivative around it has to change signs.
Okay.
Otherwise, there will not be a maxima there or an extrema there. All right. Any questions so far?
No, sir.
All right. And does that idea feel kind of intuitive? The idea that there has to be a sign change?
Definitely.
Awesome. Super glad. All right. So. All right, so one of the solutions is to use the first derivative test, what we just did. We identified a critical point, all right? And if we wanted to determine whether that critical point was a maximum or a minimum, we had to identify whether there was a sign change or not. So we applied the first derivative test. For the x cubed example, we identified there was not a sign change, so there's no extrema there. For the x squared examples, we identified there was a sign change, so there was either a maximum or a minimum there. That's what the first derivative test is. We're looking at either side to see if the derivative changes signs.
Okay.
All right. Keep in mind, this method may seem useless when looking at graphs. I mean, when we look at graphs, we can clearly see which points are maximums or minimums. All right. Because like if I'm looking at x cubed and I tell you like, is this a maximum or is this a minimum? Without any calculus knowledge, you could tell me this is neither.
Yeah.
Right. So the strength of this theorem does not come from graphs, right? Because if we look at graphs, we can easily determine where the maximum or minimum is. But it comes from being able to determine where the maxima or minima occur if you're not given the graph and you're just given the function, all right? Let's say I had no idea what the graph of x cubed looked like. I was just given y equals x cubed. And I wanted to find if there were any minimum or maximum values of the function, right? I would find the derivative and find where it's 0 or undefined to get my critical points.
Okay.
I'd realize that the only critical point occurs at x equals 0.
Yeah.
And then I could go like, okay, well then what I need to do is I need to figure out what the derivative is like if we get close to 0 from the left, and what the derivative is like if we get close to 0 from the right, all right?
Yeah.
So the derivative of x cubed is 3x squared, all right? As we get closer to 0 from the left, right, the derivative is positive. This function is positive. Yeah, remember, this function is the derivative function. So
Yeah. So it's
we care about the actual value of the function, not the slope.
Yeah.
Okay. And over here, the derivative is positive, right? So there is no sign change, all right? And just by plugging in really small negative values or really small positive values, I would be able to figure that out without even looking at the graph, right? If I were like, what is the derivative like on the left-hand side of 0? I'd be like, well, we have a negative number squared. That's going to give us a positive number, so the derivative is going to be positive. On the right-hand side, I'm going to get a positive number squared, all right? So then derivative is also going to be positive from the right. So I'd realize there's no sign change. So then the point at x equals 0 on x cubed is not a maximum or a minimum. because there was no sign change. And I could have theoretically done that without looking at any graphs whatsoever, just by using the function we're given and using some algebra.
Word.
Does that sound like intuitive, or do you need a?
Yeah, definitely. No,
Cool.
I'm totally good with that.
Cool, awesome. So I'll reiterate. The power of the first derivative test does not come from looking at graphs. It's so easy to see where a maximum or minimum will or will not be if we're looking at a graph. But if we're just given the equation of a function, that's where its power comes in, because we can use the first derivative test to figure out where maxima or minima are going to be if we're just given the function and not the graph. All right, because we just find all the critical points and then look at what the derivative is like on either side of those critical points and see if there's a sign change. And we could do that without looking at the graph and just using our function and our derivative function, which we can calculate just from having the function. All right. Any questions so far?
No.
Okay. All right. So the theorem the textbook outlines is the following, and I'll have you, and I recommend you write this down, but if not, it's pretty intuitive, so you just do whatever you want. It says, if the derivative changes signs from positive to a negative around a critical point, there's a maximum there. If the slope is positive, gets to a point, and then goes negative, you can see how that's a maximum.
Yeah.
And the opposite is for minimum. If the derivative changes from a negative to a positive about a critical point, the critical point is a local minimum.
Okay, cool.
All right. Any questions?
No.
Cool. All right. Extrema endpoints. Endpoints are a bit different, all right? Because there's no really test to be applied. And I'll explain that on Jamboard. I need to connect my thingy to the computer. All right. So endpoints are a bit different, all right? Because there's no really derivative test to be applied because we can't look at either side of endpoints, right? There's only one side to consider when we're dealing with endpoints. Okay, awesome. So let's say I'm looking at some weird function, all right? And we'll say that this is x coordinate A. I'll graph my axes, all right? And this is x coordinate B, all right? And I'm looking at the function, all right, on interval A, B, the closed interval, all right? So because it's a closed interval, we talked about this yesterday, there's going to be a minimum value, a local minimum here and a local maximum here, right?
Yep.
Because the endpoints are at a low and the endpoint is at a high, a relative high. And because it includes the endpoints, there's not going to be a hole there, so we will have a maximum there, all right?
Yeah.
So the rule for figuring out whether an endpoint will be a maximum or a minimum is a little bit different because there is no first derivative test to be applied because we can't look at a sign change on either side because the other side we don't care about, all right? So the rule for figuring out whether an endpoint is a maximum or a minimum is a little bit easier. So first of all, if we're dealing with an interval, it has to be closed. Otherwise, there will not be a maximum or a minimum there. Remember we talked about that yesterday?
Yep.
Okay, cool. And additionally, for there to be a maximum, the derivative around it has to be positive. Oh, wait. Actually, let me backtrack. That is not correct.
Is it the other way around?
No. It is right, but there's different rules for the different endpoints, all right?
Okay.
Because you notice here the derivative around it is positive, right?
Yeah.
But here the derivative around it is positive too, and this is a maximum and this is a minimum. So there's different rules for what endpoint you're dealing with, all right?
Yeah.
All right, so let me backtrack. I forgot about that one thing. Forget about what I said. So it's still right though. The first point is still right. The interval has to be closed, otherwise the endpoints cannot be maximum or minimum. If we're dealing with the right endpoint, or why don't I start with left because we read left to right. Left endpoint, all right? If the derivative is positive, then it's a minimum. And you see that here, right? We have a minimum here, and the derivative around it is positive. The
Yeah.
slope is positive. If f prime is negative, we have a maximum, right? Let's say this was our endpoint on the left and we had a negative derivative around it. You can see how it would be a maximum.
Yep.
Cool. And this is for the left endpoint. This rule only applies for the left endpoint because you'll notice for the right endpoint, the rules switch.
Yeah.
Okay, cool. So I can write it out, but you can probably figure it out already. Right, if the derivative is positive, we have a maximum. And if the derivative is negative, we have a minimum.
Yeah.
Here we have a positive derivative and we have a maximum. If we had a negative derivative curving down, let's say this is our endpoint, then it would be a minimum.
Yeah. That's very intuitive.
Cool. Awesome.
Yeah.
Uh-oh. All right. So yesterday when we were talking about endpoints, right, we were mostly considering endpoints to a function's domain, right?
Yeah.
Like, for example, that's a terrible... What? I need to quit math and learn how to draw my axes. But yesterday, when we were considering endpoints, we were considering endpoints to a domain, and we're doing the kind of the same thing there, right? When I established the interval a to b, right, we drew a function that was only defined from a to b, all right? So this is its domain. Every single function I've drawn so far, the interval I've been considering has been its domain, right? Because this is the only place where the function is defined.
Yeah.
I haven't drawn any other function over here, so a to b is its domain. You agree with that?
Yeah.
All right. However, I will say that doesn't always have to be the case for our rules to work, all right? The function could be defined all the way on and on and on, all right? All the way on and on and on. And we could be just considering AB, all right? Let's say we're just considering some random interval, all right? Obviously, the domain of this function goes on forever, but let's say we're just considering this interval and we want to figure out the maximum or minima, right?
Okay.
All right?
Yep.
When we're just considering this interval, we only care about the values in between A and B and including A and including B, all right? So even though, all right, B is not a maximum, because for the whole function, right? Because it goes on over here.
Yep.
On the interval AB, it is, because we're only looking at the interval.
Okay, yeah.
So even if the interval we're considering isn't the function's entire domain, but rather just some random interval, the endpoints could still be maxima or still be minima with the rules we've established, regardless of what happens on either side. Because we don't care what happens on the other side, we're only considering what happens in the interval.
Yeah.
All right? So it doesn't just have to be like, the interval we're considering doesn't just have to be the function's domain. It could be any interval we choose, and the rules would still be the same. All right. We good with that?
Yes.
All right. Any questions?
I'm all good.
Awesome. You're doing great. You're doing great. All right. Okay, I'll read this, and I think we covered it already, but endpoints are a bit different. If we were looking at endpoints to a function's domain or just the endpoints of some interval, the only values we are considering will be either to the right or the left of the endpoints, right? We're only considering values to one side because they're endpoints. Hence, the criteria for the endpoint to be a local maximum or minimum is a bit looser, and the rules I established below are the ones that I just covered with how to determine whether a left or right endpoint will be a maximum or not, or minimum or whatever. All right. All good to move on?
Yeah.
Any confusion, any questions?
Nope.
Cool. Awesome. Dylan's step-by-step guide to finding a function's extrema. Patent pending, as obviously.
Yes, sir.
Okay. So, step one, right? Calculate the derivative of the function. And if you want to, let me know if you're going to write this down or if you want to take a picture of it, because I would recommend it's a useful step-by-step guide.
Okay, sure. Yeah, I'll do that. Yeah, I'll take a picture. Actually.
Okay.
Got it.
Cool. All right. So calculate the derivative of the function. Step 2, set the derivative equal to 0 and solve for x. And then step 3, find all of the values of x that make the derivative undefined. The reason we're doing this is because the x values we found in step 3 and step 2 are going to be our critical points.
Okay.
In order to find our critical points, we have to do step 1 first, because we have to set the derivative equal to 0 or undefined. So step 1, 2, and 3 is just finding the critical points. Because those are all the possible points where extrema could exist.
Yeah.
Step 4, apply the first derivative test to each point. And to do that, plug in values really close to the x value of the critical point from both the right and the left-hand side of the derivative function.
Okay.
All right? Basically, if the point passes the first derivative test, plug it into the original function to make sure the function is defined at that point. That's a mouthful, but we'll explain it later. If it is not, then the point will not be an extrema, which more on that in the next slide. All right, let's look at this step with y equals x squared. All right, just so I can illustrate step 4 because it was kind of a mouthful. Okay, cool. So why don't I just give y equals x squared, and we're not going to draw the graph, and we're just going to try and find its maximum or minimum, imagining we had no idea what it looked like, using my step-by-step guide. Step 1 tells us we have to find its derivative, 2x, done. Step 2 tells us we have to set it equal to 0 and find the x coordinates where the derivative is 0, and that's obviously x equals 0.
Yeah.
All right. 3, we have to find out when the derivative is undefined. There's no value for x that will make this derivative undefined. So we can ignore step 3. All right. Step 4 tells us to apply the first derivative test to each point. All right. Yeah. So we notice we have a derivative of 0 at x equals 0. All right.
Yep.
So we have to consider what the slope is going to look like from the left-hand side of 0 and the right-hand side of 0. From the left-hand side of 0, we're going to get 2 times a negative number, right?
Yep.
Which will give us a negative number.
Yeah.
From the right-hand side, we're going to get 2 times a positive number, which will give us a positive number. So that's the first derivative test. We evaluate what happens if we plug in x values from either side of each point to the slope.
Yeah.
And we notice that there is indeed a sign change. On the left-hand side, we'll get negative numbers. On the right-hand side, we'll get positive numbers.
Yeah.
So this tells us from our criteria that it passes the first derivative test and there's a minimum there.
Okay.
And the last step is we have to make sure that the point x equals 0 is actually defined in the original function. All right.
Yeah.
Because we solved the derivative function, right? So even though this is defined in the derivative function, it doesn't necessarily mean it's going to be defined in the original function. So we just have to triple check that x equals 0 is a valid point in the original function, and it is.
Cool.
All right. Does that my step-by-step guide make sense?
It does make sense.
Okay, cool. Awesome. So I'll go on to Desmos and illustrate a point. All right. The reason we have to check to see if the original function is defined at that point is for the following reason. All right. Let's look at the graph of 1 over x squared. All right.
Yep.
The derivative, I'll just do it very quickly. The derivative is, I believe, negative 2 over x cubed. All right.
Yep.
So if we're trying to find maxima or minima of 1 over x squared, all right, we have to find when is the derivative equal to 0 or undefined. So the derivative is never equal to 0. I'll get rid of the first function so you can just see the derivative function. The derivative function is never equal to 0. It gets closer to it, but it never actually equals 0.
Yeah.
But it is undefined at x equals 0.
Yeah.
So a critical point of the original function will be at x equals 0.
Okay.
So the next thing we have to do is, well, we found a critical point at x equals 0, right? Because that's when the derivative is undefined.
Yeah.
So then we have to apply our first derivative test. Well, look, the slope from the left-hand side is positive, and the slope from the right-hand side is negative.
Yeah.
So this passes our first derivative test. We found
that you need to plug it back in.
Yeah. Yep. So we found that the derivative is undefined here, and it passes our first derivative test. So our criteria is telling us that there should be a maximum here. But is there a maximum there?
No.
Exactly. So that's why it's vital that you have to plug in the critical point you get back into the original function to see if it's even defined there. Because if it's not defined there, how can there be a maximum there?
Yeah, exactly.
All right.
So if it's undefined because it's a tangent, then it like will probably. But if it's undefined because it's going to infinity, then it won't, obviously, because there's no point there.
If it's undefined because of a yes.
Cool.
Actually, I'm not sure. So tangents, yes, maybe, but the main case where an undefined derivative would produce a maximum is when we have a weird function that looks like, or when we have a cusp or a corner. All right.
Okay, right.
For actually, here's a perfect.
A tangent's going straight up, so that doesn't. No, it's not.
Like for example, the derivative is undefined here, but there's no maximum or minimum here.
Yeah.
So I can't say all of them, but for most cases, a vertical tangent, we have to be careful, because it probably won't produce a maximum or minimum.
Okay. Yeah.
All right, but I will say that, so this is just the absolute value of x. All right, the derivative is undefined here, and we have a minimum value. All right, so here's a real life example of not a weird function. This is a function that we're very familiar with, being having undefined derivative and being a minimum. So that's an example where the derivative could be undefined. And so the derivative is undefined at x equals 0, but the function is defined at x equals 0. So that's a scenario where the derivative could be undefined at a point, but the original function could be defined there.
Okay.
But in our previous example, we found that the derivative is undefined at x equals 0 and the original function is undefined there. We have to make sure that the original function is not undefined. So you always have to triple check. It's a lot of triple checking, but that's that. All right. Good on that?
Yeah.
So once you applied that test, you apply the first derivative test, make sure that the critical point, if you find a point that should be a minimum or a maximum, make sure it's defined at that point, the original function. All right. If you've done that and you find it is defined and it passes all the criteria, all right, then there's a maximum or minimum there and you're good to go.
Yeah.
Then the final step is consider the endpoints to a function's domain, or if you're looking at an interval, for example, consider the endpoints to the interval you're considering. All right. So just apply the derivative test for endpoints to see if your endpoints will be maximum or minimum, and remember that it has to be a closed interval you're considering, otherwise they won't exist.
Yeah.
All right, and that's it. And I hope you can realize that we could do this step-by-step process without even looking at the graph. Just by giving the function, we can apply this process and figure out where the extrema are.
Yeah.
That's where its power. That's where its true power lies.
Cool.
Because obviously we can look at a graph and see where the minima or maxima are.
Pretty easy to look at.
Yeah, exactly. But its true power arises in if we're not given that, we can figure it out using calculus and algebra.
Cool.
All right. I think the meeting's going to end shortly, if I'm not mistaken.
We got 5 minutes. Yeah.
Okay.
I think do you want to do the practice?
Yeah, that's a good idea. Yeah. Let's find the extrema of this function.
Okay.
All right. So I'm going to go into Jamboard and do it real quick. All right. Hopefully it won't take me 5 minutes. All right. So let's find the extrema, and I'll walk through it, and so you can kind of see me going through the process and understand what's going on. Let's find the extrema of x squared plus 2x over x minus 1, right?
Yeah.
So step 1 is to calculate its derivative. Do I really want to do that, or can I just... Obviously, we could calculate the derivative of this function. We know how to do it, but that's not the point of this. So I'm just going to plug it into a calculator.
Okay.
Because obviously, yes, we know how to do the quotient rule and find the derivative of this, right? But
yeah,
for time's sake, I'll just skip that step, all right?
Okay.
But obviously, without a calculator, we still know how to do this.
Yeah.
All right, cool. Is that fine with you?
Absolutely.
No, it's not what I wanted. Come on. Oh, Jesus Christ. I'm joking. All right. So, x squared minus 2x minus 2 over Wrong thing, wrong tab. X minus 1 squared. Okay, cool. So step 2, if we want to find our critical points, we have to figure out when is the derivative undefined or 0. So obviously, the derivative will be undefined when x equals 1, because we'll have a denominator of 0.
Yeah.
So our first critical point is at x equals 1. But immediately I can eliminate this critical point from being one of our possibilities, because x equals 1 is not defined in the original function. So even if I found out that this point passed the first derivative test, if I plugged it back into our original function, it wouldn't be defined there. So I know that this cannot be where an extrema occurs.
Yep.
Cool with that?
Yes.
All right. So the only point we have to consider is when the derivative is going to be equal to 0. And it's going to be equal to 0 when the numerator is equal to 0, right?
Mm-hmm.
All right, equals 0. And we could use the quadratic formula to solve this, all right? Obviously, we know how to solve this quadratic, but I'm just going to plug it into Desmos for time's sake because it's not an algebra course. We know how to do that. Not too concerned. All right, so it's going to occur at negative 0.732. And 2.732. So here are our 2 critical points we have to examine. And these critical points will make the original function defined. So these are legitimate points we have to consider.
Yeah.
All right.
And since those are points when it crossed 0, that means it like goes from being positive to being negative, right?
Yeah. So what we would have to do, and I know we're running out of time, and I'd probably spend more time on it. What we would do is we would look at our original derivative, right? And we would look at one point at a time. All right. So we'd first start by considering 0.732. What I do is I plug in negative 0.731 into the derivative and figure out what sign it is, if it's negative or positive. Then I plug in negative 0.733, all right, and figure out what sign it is. Right? I'm taking 2 numbers really close to the critical point on either side and seeing if there's a sign change.
Yeah.
All right? And if there is, then I know there's a maximum or minimum. So that's the process we'd follow. Okay. We take numbers really close to our critical points, see if there's a sign change. If there is, then we have a maximum or minimum. We just have to identify it.
Okay.
All right? Cool. All right, so I think the meeting's going to time out in just a minute. But I'm going to stop recording, and I'll be back in just a second for YouTube. So thanks for watching this video. I'll see you guys in the next video.